Hello, everyone. Welcome to a discussion which is called Numerical Faithfulness and Failure Modes in Financial Retrieval-Augmented Generation System. And I'm Toby, and this is from Toronto Metropolitan University. And so, what is a RAG? Let's look at the basic RAG pipeline. And the idea is as follows. Suppose there is like the user asks a question, what is Apple's revenue in the year of 2024? And the next step would be, let's assume there's some sort of a knowledge base. Let's say it would be maybe a PDF of the filling in 2024 of some other tables or reports. And the retriever, BM25 or some other retriever, will give slightly more detail on that. This will basically search the knowledge base and retrieve relevant chunks. So basically, the document is like, because the document is so big, then we have to divide them into chunk. Like each chunk probably just a bunch of sentences. And after we retrieve the top K chunks or top K documents, we will basically feed into a large language model. And the large language model will use the documents to generate an answer. And you will basically produce the output. And the generating answer is returned to the user. And retrieval augmented generation was invented because large language models sometimes they hallucinate and they invent stuff. And if we give them the knowledge base, then it's less likely they'll produce hallucinated content because they can retrieve relevant document first and then generate an answer using the retrieved evidence. And so this will allow the LLM to not rely on just the internal memory. Now, what is a RAG? So we'll give some formal definitions. It basically combines what we call information retrieval. It's like basically we search a knowledge base for relevant documents that are very similar to the query. And for example, BM25 and also some other dense retrieval method. And large language models, basically we give the retrieved documents to it and it will generate an answer grounded in external evidence, ideally. And why do we need RAG? Because LMs they often hallucinate facts, and sometimes the model knowledge may be outdated. If you remember the early days of ChatGPT, if you ask a question like in 2020, you may say, "Well, my training data is only up to 2019." And also, domain-specific information may not be stored in model parameters because it's trained on general knowledge. And if we ask like very specific knowledge, like medical stuff, it may not be able to answer. And also, retrieved evidence can improve transparency and traceability. Like, if we ask the model, maybe where did you get this information, it can actually be better for the user. And so, the pipeline basically, there's a question, we retrieve the evidence, and we generate an answer. Yes, I will send a link to the slides. Let me just do it now. Eh, and this is the link to the slides. Perfect. So, what problem are we solving in finance? And let's give an example. Perhaps, so for example, what is the percentage change in revenue from 2010 to 2011? And this is where what typical problem we are solving. And let's suppose we retrieved evidence is 2010 revenue is 63K and 2011 revenue is roughly 23K. And the correct answer should be just using this formula, just calculate the percentage change. And the right answer may be something else. And we want to be able to sort of compare the two answers in a nice way. And so why is financial reg very challenging? The first problem is that answers often require very exact numerical values, just we demonstrated in the previous slides. And many questions require arithmetic reasoning. And finance tables, because tables are actually very difficult to process because you have so many rows and columns, and it's very hard to convert into natural language stuff. And small numerical mistake can lead to very different conclusions because we know that if we perform many calculations and the errors could accumulate and your answer may be deviate a lot from the true answer. And the core challenge is that a RAG system should be able to retrieve the correct answer but it should be able to produce the numerical answer, but sometimes it doesn't. And this motivates our study of what we call numerical faithfulness in financial retrieval-augmented generation. Let me see if there's a question. Okay, I will do it again after the presentation. So why does traditional metrics fail? So let's look at the same example again, and we have the same pipeline that we talked about in the few slides ago. And traditional metric, for example, exact match, probably exact match, the two numbers probably will match, we probably give a zero. And rogue token of one, this is basically measures the token overlap between the model answer and also the ground truth answer. And let's say the model outputs some also natural language. Let's say the change in revenue was like minus 52%, like and the ground truth, let's say, is the change of revenue was minus 62%. And the token F1 may be very high because the answers they have very similar texts and contains gold. The gold numbers are actually mentioned. So let's suppose that the model actually correctly retrieved the two numbers, and so it actually contains gold. And as a judge, maybe the large language model thinks the answer is mostly correct because the answer looks plausible and is grounded. So we can see that the traditional metrics doesn't tell the whole of the story because it doesn't consider the numerical aspect of it, and we will give concrete examples of how the aspects of numerical faithfulness. So the takeaway is that traditional metrics they mostly focus on textual similarity, and perhaps they may give a high score even though the answer could be wrong. And we need metrics that check numerical correctness, arithmetic validity, and also grounding of numbers. And so this is just a textual explanation of what I just said. And there are also a group of metrics that measures the retrieval quality, like for example, recall and precision. Basically, there's the golden set of retrieved documents, and there's the retrieved documents done by the say the LLM, and we can do some comparisons. However, the issue is even though if you may retrieve the correct document, your final answer could still be incorrect, such as because your computation process is incorrect. So existing metrics they do not verify is the final number correct, is the number grounded in retrieved evidence, and was the arithmetic performed correctly. So the research question we are happy to answer is as follows. The first one is how numerically faithful are financial reg system? The second question is can we categorize different numerical errors? And the third question, do conventional metrics hide numerical inconsistency? And finally, can we add some sort of a lightweight verification to identify unreliable outputs? And now let's give a concrete definition of numerical faithfulness. I decided to include a triage. Basically, I decided to divide into three components. The first component is grounded. So basically, the answer is supported by the retrieved evidence. So let's say the model claims that the revenue for, say, 2021 is 63,000. We should be able to locate this number from the retrieved document. The second aspect would be arithmetically valid. Basically, if let's say you want to compute the operation 23,000 minus 63,000 times 100%, you should be able to done the computation correctly and produce the right number, like minus 63% instead of minus 52%. And finally, the accuracy, the answer produces by model should be able to match the ground truth numerical answer. And the key takeaway is that grounded doesn't mean numerically correct because there's some errors that we'll talk about in the next few slides. And so numerical faithfulness is basically encompassing all three aspects. And so that's the textual explanation of the previous diagram. Accurate means the answer matches the ground truth. Grounded means the answer is supported by the retrieved evidence. Arithmetically valid means the computation and reasoning process are correct. And in general, grounded doesn't mean the final answer is going to be correct. And so now let's give a formal categorization of the numerical failure. And there are six of them. We'll give example for each. The first one is what we call retrieval-induced errors. So let's suppose what we asked, what was the revenue growth from 2022 to 2023? And let's say the retrieved evidence was actually 2021 and 2022. So you know that the answer is definitely not going to be correct because the required 2023 revenue was never retrieved. So the idea is that bad retrieval will going to lead to bad reasoning. The second category is what we call arithmetic computation errors. So let's suppose it's the example earlier, basically the change in revenue. Let's say for some reason it performed the calculation incorrectly and outputs like minus 52% instead of minus 62%. And this is what we call the arithmetic error. And correct evidence, this is just wrong computation. And we know large language model, they are bad at numbers. The third failure type is what we call substitution error. So let's say what was the company's net income? Let's say the retrieve evidence, the revenue, the net income, and also the operating income. And let's suppose the model produces the answer as 30 million, and we know that the item is incorrect because the model selected the wrong number from the evidence, because this is asking the net income and not the operating income. And this is the example of a correct retrieve evidence, but the wrong numbers obtained. The fourth type is what we call unit and scaling errors. Basically, so this is basically a mismatch in units. So let's suppose the retrieve evidence saying that the revenue was 2.4 and all figures in billions USD. But let's say the model say, oh, the revenue is 22.4 million. So clearly the units are not matching. So the problem is the number was actually correct, but the scale and the unit is incorrect. The next category is hallucinating numerical values. This is a very easy one. And so let's say the model answers the revenue is 135 million and the number never appears in the retrieve evidence. And so perhaps the model decided to invent a number, and this is what we call hallucination. And the sixth category is abstention despite relevant evidence. This is where what happens if the document is too complex and the retriever is not good enough. So let's say the question is like, what was the company's revenue? And let's say the retrieve evidence actually contains the answer, but the model decided to say insufficient information. And the problem is the answer exists in retrieve evidence, and the model refused to answer. And so typically, this is the case where evidence is available. It may even be available in the unretrieved documents, but the answer was not produced. And any questions here?
Yeah, just quick question. So, what is a typical case? If we go to the previous slide, what typical case model will output no answer whenever the RAG provide the correct context?
If let's say if the retrieved document could be too large, and let's say this line is embedded in a table, then sometimes the reg could not figure it out. If it's like plain text, then there's a very good chance that we'll figure out is the correct number.
Oh, okay. Yeah,
Mm.
because I had the similar situation when I use Llama. Oh, sorry, that's some local model. Yeah,
Mm.
but yeah. But that was impacted by my instruction part. I say so if there's some condition, just answer no. Yeah.
Mm-hmm. Yeah, that sometimes depends on the prompt as well.
Oh, Jammer 4. Yeah, Jammer 4. Now I remember.
Mhm.
Local Jammer 4. But go yeah, I'm done. Yeah, go ahead.
Any other question?
One question that
Yes.
is more related to the presentation. The presentation is numerical faithfulness,
Yes.
but the types of failure is the lowest on LLMs, like the numerical faithfulness, like mostly abstention and hallucination dominate, right?
Yes, hallucination. This is but we also restrict the discussion to hallucinating numerical value. Here we're not talking about the general hallucination.
Yeah, this, yeah, okay. So all of them kind of means numerical
Yeah.
faithfulness or
Yes. Yeah.
and I think one of the problems is like document indexing, mostly chunking. Where would it be? Where would that fit? Or like, is it just an information retrieval problem? Because when chunking, you might cut the table header or
Yes.
those kind of situation. Like the LLM can't have that information for like some parts of the table, let's say, or
Mm. Yes, so basically, yes, the presentation is basically to address a gap in the research, and the presentation is not designed to propose a solution, but rather to identify the problem. It's basically we are trying to design a bunch of new metrics to ensure the evaluation is more fair for these numerical problems.
okay.
Yeah. So let's look at the how we run the experiments. So basically, I decided to be very simple because the paper is mainly for identify the research problem, and the experiment is not a major component. So we'll keep it simple. We'll use two retrievers. The first one is the BM25. So this is the very classical information search algorithm. Basically, this scores document using the keyword frequency and also rarity. Think about like TF-IDF stuff. And documents containing important query items, typically they get higher scores. And this is widely used in all of the search engines and enterprise search system. The second one is the keyword search. This is basically exact keyword matching and will retrieve passages that contain the query terms. And this is the a simple retrieval baseline. And for simplicity, we'll try K, basically the number of talk documents to be 3, 5, or 8. And the generation stage is just a regular rack. We give the retrieve passage to a large language model. Here we just use one. This is pretty good to run on a Mac and doesn't get all of the RAM. And the example output should be some sort of a natural language with numbers. And we evaluate the generated answer using conversion metrics such as exact match, ROUGE. ROUGE basically measures the textual, the token overlap, and contains gold means if the generating answer contains the gold number. And we also look at different numerical faithfulness metrics such as numerical match, relative error, like what is the error between the output number and the goal number, and grounding metrics, and also failure taxonomy analysis, which we'll briefly discuss in the next few slides. So the goal is to measure not only answer quality, but also numerical reliability. And dataset, we decided to use the FinQA dataset. So this is a financial question answering benchmark designed to evaluate numerical reasoning. And this is a dataset basically consists of like PDFs, but they process the PDFs. The PDFs also contain tables as well. And these are typical financial reports and also SEC filing excerpts. And it consists of natural language question and also ground truth numbers and also ground truth retrieved nuggets. And the example question is what we give already, and why FinQA? Because this well, it requires retrieval and it requires numerical reasoning, and also requires some sort of arithmetic computation. We will need to reformulating FinQA as a RAG task because the FinQA assumes the model has direct access to the evidence because it gives one of the field in the data set is actually the golden evidence. And what we did is we basically we convert financial text and tables into basically into a big passage, and we sort of build a very simple chunking method, and we retrieve topic K evidence using BM25 or keyword search, and we generate answers using the large language model. And the goal is to evaluate how retrieval quality impacts numerical reasoning and answer reliability. So table linearization is a very important problem because many of the financial information is often stored in tables rather than sentences. And the challenge is that retrievals are typically designed for text stuff. However, tables may contain row labels, column headers, and cell values, and important relationship may be lost during pre-processing. And a naive conversion may be just do a row like revenue 2010 63K, but the improved conversion could be like revenue in 2010 was 63K, and this still only kind of deals with simple tables, and it probably will not work for complex tables. And the benefit is we want to be able to preserve the relationship between labels, years, and values. And the evaluation metrics is as follows. The exact match basically is the generated answer identical to the ground truth. And contains code means does the answer contain the correct value? And token of one basically measures token overlap between answers. And the limitation is these metrics focus on answer similarity, not numerical reasoning, especially if the golden answer is only a number and also doesn't contain if it doesn't contain like text. And numerical faithfulness metrics. This is the metrics we propose. The first one is the numerical match. This is basically saying does the generated number match the ground truth? And relative error basically measures how far the prediction is from the correct value. And direct rounding score basically means is the generated number present in the retrieved evidence. So the model will generate an answer that potentially contains many numbers because we want to be able to see the reasoning process. And any number grounded means did the number use at least one retrieved number? And if yes, this will return 1. And the goal is to measure numerical correctness, grounding, and reliability in a very simple way. And so we see that the exact string metrics are pretty low, but we'll see that numerical metrics could reveal a bit more structure. And here we are looking at hold on a second. So this is the retrieval strategy result for all the 6 combinations with BM25 and the different top K parameter. And we can see that no single retrieval setting dominates across all metrics because these retrievals are still very simple. But we can see that the grounding is actually not that bad. So recall that grounding basically means is the generated number present in the retrieval evidence. So we can see at least about half of the numbers that actually we can find in the retrieved documents. And so top K trade-off, this is a very important parameter. If we give it a very high top K, it may introduce irrelevant numbers, distracting context, and also conflicting values. And this could introduce higher risk of operand substitution. And the main finding is that more retrieved context does not necessarily lead to better numerical faithfulness. And we see that the grounding score actually reduced, even though the non-match actually increased. And finally, we look at the improved preprocessing for the table linearization. So we can see that after we apply the table linearization, all the metrics actually improve. For example, the num-match actually doubled. And removing year bonus actually substantially improved the numerical match because previously we sort of give the year, we probably emphasized too much the year label to the table and actually doesn't improve the result much. And the key finding is that grounding scores are often much higher than numerical match scores. This means that the model may be able to retrieve relevant numbers, but the generated answer may cite or use retrieved values, but the final computation can still be wrong. So the idea is that grounding is necessary but not sufficient. Here we look at the error distribution for BM25 top 5 and BM25 top 8. So we see that increasing the top K to 8 actually reduce the abstention problem, but it also increases the hallucinating number. And so basically the percentage of hallucinating number actually increases. And correct but the weakly grounded means the answer could be correct, but the grounding is not completely right because it may cite sometimes irregular numbers. And grounded but incorrect, we see the ratio actually decreases. and arithmetic error, they stay on the similar level. So we see that top 8 actually reduces abstention but increases hallucinating numbers. So here the abstention sometimes includes cases where the answer actually present in the document, but the model sometimes did not retrieve the relevant chunk. Finally, this is the example we gave earlier, and we will not go over it again. And finally, we'll just do some simple, lightweight verification. And so this is a way to sort of check the answer post hoc before we even return the answer to the user and sort of try to flag suspicious answers. So this is a very simple case. Basically, we only talk about for percentage change questions. So let's say we retrieve the passage contains 10 different numbers. We'll try to it depends on the query. We'll do the operation. Let's say the query asks for change, then we'll do the minus operation, and we'll try all the pairs of numbers. And let's say they will produce 10 choose 2 and number of answers, and we compare all the answer against the generated answer. And if none of the answer matches the generated answer, we'll flag as suspicious. And if one of the answers matches the generated answer, we'll flag as verified. And this is kind of as a very simple diagnostic tool and it's not automatic correction. And we did some simple experiments and it showed that out of the 73 attempted verification, the verified rate actually increases from top 5 to top 8. And the interpretation is that verification can identify arithmetically consistent outputs, but it cannot guarantee semantic correctness. And operand selection still remains a very difficult problem because, like, there are so many operands like plus, minus, and also bracket stuff. Finally, what is the lesson for our engineers? So, do not evaluate drag with only text metrics, and we should treat retrieval and reasoning as separate failure points. And table processing actually matters a lot, and more context sometimes can hurt numerical reasoning because of the lost in the middle problem. And verification is actually useful for flagging, not simple auto fixing. And the conclusion is that the financial reg system can retrieve relevant evidence while still producing raw numbers. And the contribution of this discussion is the formal framing of numerical faithfulness, automatic numerical evaluation framework, empirical analysis of failure modes, and also a lightweight verification study. Future work, we definitely should explore better table area retrieval, stronger arithmetic verification, and some sort of operand selection models, and maybe even multi-document financial reasoning. And maybe we should create a benchmark for numerical faithfulness. And any questions?
Uh, I have a question.
Hmm?
So for the retrievals, we have BM25 and keyword search, which is both lexical retrievers, and the EM is very low. So 0.01 to 0.04, I guess.
You mean exact match?
Exact match, yeah.
Yeah,
So
because it's a very simple retriever, so it's probably gonna perform very well because we didn't explore the dense retrieval just to make experiment simpler.
yeah, so my question is there a dance retrieval or like I mean the first site the list dance retrieval as well, or like re-ranking or other retrieval how do you say methods, or is it only dance retrieval? Uh, Sorry, is it only lexical retrieval? And does the retrieval also contribute to the like correctness of the uh, solution? Like how much is the financial reg? How much is the retrieval problem?
Here we are not trying to evaluate which component contribute the error. We are just trying to, evaluate different metrics. But in general, yes, better retrieval method will produce a higher score for EM and also contains and also non-match. Yeah, but this is not the focus of the thesis. Any other questions?
But there was this verified uh, part, and is it possible to also check how much percentage is factually correct?
You mean what do you mean by factually correct? Like to check if the numbers appear in the document?
Like the calculation is the correct, like as you said, there are different operands or like
Yes, there should be a way to do it.
this
Typically,
is just trying to understand. This is like arithmetic constant output, but might not be the correct answer.
yeah, it might not be the correct answer. This is only to try to flag suspicious answer, but it doesn't mean the verify doesn't mean the answer is actually correct. Verify simply means that the answer is plausible from the retrieved documents, but it doesn't taking into account if the retrieved evidence is even correct.
Maybe it is like an indicator that the unverified things are most likely incorrect.
Yeah, you can flag incorrect cases, but if it says verify, it doesn't mean it's necessarily correct, but it definitely can flag incorrect cases.
Yeah, yeah.
Just quick question.
Yes.
Just thinking, how do we use this as a product? So for example, if the reg plus LM generate something in output, and we find it's unreliable, so do we ask the reg to try to retrieve another set of information and let LM to regenerate and maybe compare? Okay, maybe the second round generate like a better answer, so that we choose the second round. I mean, how do we use this from the user's perspective? Yeah.
From user's perspective, this is mostly a benchmarking process. So let's say we have designed a new, RAG pipeline, and we want to, compare against the state of the art. And these metrics are actually very useful because the numerical metrics actually complements the other textual metrics. So this is more for benchmark purposes. And yeah, definitely, I think it can be used in the testing phase of your product, like yeah, it can be used. Let's say if if the metric says the computation is incorrect, definitely we should ask the LLM to calculate again. Yeah, I think that's a very plausible application.
Okay. Yeah, good. I think I read something recently. Yeah, another area of research is to be able to use AI to evaluate or whatever method to evaluate the output and select which one looks better. So kind of a filter, yeah, or selection. Yeah,
Yeah, yeah, yeah, yeah.
yeah.
Any other question?
So, do abstention failures also have false positives? Like the let's say LLM was correct to abstantiate, let's say, because there are not grounded.
Yeah, or abstention, yeah, sometimes it's false positive because sometimes we find that the evidence actually appears in the document, but the model somehow did not retrieve it.
Yeah, I'm asking this because it's to the percentage is the biggest percentage. Maybe it, yeah, obviously that's the biggest vector, but like maybe it's overblown a little bit.
Yeah, this is big because the retriever is very simple because we didn't test a better retriever, and if you use a better retriever, this I think this number will go down definitely.
Yes, makes sense. Yeah.
Mm, cool. Any other questions? Let me now share the slides. Just 1 second.